And if we want to talk about initial fluids in place, like one of the participants was asking about how do we calculate initial fluids in place, for example, initial gas in place. We usually write the term G as SB symbol, and initial condensate in place, which we would call N, assuming there's no free oil. And what we have is the geologist hydrocarbon pore volume. How do we get these two numbers? So the G, what would be in your black oil model or your true sellable gas volume in place, that would be hydrocarbon pore volume divided by BGDI at initial conditions. But there are no books that give us this equation. What's the equation for that? There are no books out there that give you that equation. The phase behavior monograph does, but no reservoir engineering books. So we got to figure out what's this. And then N is just going to be G times the initial OGR, 50 stock tank barrels per million. The initial, you might call it initial solution, or just the initial oil gas ratio. But you have to be careful here because when you use conventional gas material balance in gas condensate reservoirs that we're going to talk about later today, probably, where we use the two-phase Z factor that you've seen in PVT reports, this is not the G that they're talking about, because this is actual true, what we're going to call dry gas, sellable dry gas, not fake wet gas. Okay? But the equations that you have in the book for BG, you have the initial Z factor, you put it in to this equation here. Okay, this one up here, where it was? Yeah, this one here. When you go to this equation, you put in Z at initial pressure, initial pressure, and Z at initial, you don't get the right BG. You don't get the right 900 TCF.
You don't get the right sellable gas.
You don't get the right sellable gas. You get some kind of fictitious wet gas. So we need to figure out how to get this processed dry gas volume factor. Of course, the CGR, initial CGR, we know that. Okay. So this will normally come from a PVT, a black oil PVT table, as will also that number, because it depends on the multi-stage surface process. So the black oil PVT table, we're going to need to look at that. It will give us both the BGD numbers, also at initial conditions, and it'll give us the solution oil gas ratio. So now we're starting to talk about what is a black oil table for a gas condensate. It's not something you get from the laboratory. The laboratory does not give this to you. The only way to get that black oil table is from an equation of state, practically. An equation of state model. So now, when we get to the PVT part of the course, which is today and a little bit on Friday, we have to talk about the equation of state model. For gas condensates, you cannot do gas condensate engineering without an equation of state model, period. So we have to go there. We can't even calculate the initial gas in place and the initial condensate in place without that table. We're in trouble. You know, in reality, from the PVT lab, yes, they probably do give you almost enough to get the BGDI and the little RSI. So you can probably do that with the lab report, but maybe not for this surface process that you actually want to look at. Very well not. Okay. So what we're going to do now is that we're going to actually look at this process system and how that relates to an incoming well stream composition and how that composition is processed into the two products, surface gas and surface oil. So that's basically what we want to try to look at. And we want to come up with a means by which we can move back and forth between a molar composition or some approximate, you know, part of the molar composition and the oil gas ratio. So what to do that, what I'm going to do is I'm going to try to kind of explain, if we look at this process of incoming moles of the different components, I'll write it in WI for well stream, like that, and then we operate with moles of total product gas and moles of total product surface oil. A program like HYSYS actually operates on all this molar basis. Even the multi-stage calculations in a PVT package does this, but you don't usually see the number of moles being provided. So what we're going to do is that we're going to say, let's define a recovery factor of a given component. And what we know is that if we can get more of that component in the surface oil phase, we'll get more value for that component, okay? Because we generally get a higher value for our condensate product than our gas product. So as many of those components we can get into the surface oil condensate, the more value we make. So I'm going to define just a recovery factor of the incoming well stream into what goes into the surface oil. So that would be given like this over what comes in. And then I'm going to kind of sketch for you how that would look for individual components. Was there a question or comment?
Some of the jobs.
So and here we're just going to put, of course, all your non-hydrocarbons are going to be going into the gas pretty much, even methane, ethane, propane, butanes, pentanes, hexane, and then we've got C7, C8 on out. Okay. So if we look at, let's just say that we did the most inefficient process we could probably use in reality is a single stage flash to standard conditions. So we go to low pressure, and a lot of the heavier components actually get vaporized into the gas. So we get a fairly inefficient. So let's just use some colors here. We'll use this color here, whatever. This will be single stage flash, like that. Okay, and okay, so that's a very inefficient process because you get a lot of these heavier, light heavy components that are still not making their way completely down into the oil phase. If we then go to a, let's say a multi-stage flash, 3 stages, and I think what we're using for this CUF paper is 1000 psia, 80 Fahrenheit. I'm not sure what the second stage is, and then we'll look at that and we'll get something that's more efficient. I'm not going to change much here, but probably this thing will come up like that and something like that. And then if we actually maybe even create multiple liquid products, or we start putting dew point controllers on the gas and we extract out liquids from the gas and so forth and so on, we may get something that's, I'm just going to call it high cis, a really efficient process in stage plus plus. You might get something that's even more efficient, like that. Okay. So you can use an equation of state to kind of calculate all of this, and in fact these recovery factors will be relatively independent of the incoming well stream to some extent. But it's still kind of a heavy calculation to convert molar streams to the two products, and then converting the product molar amounts to mass and volumes. A little bit complicated. So what we're going to do here is say that we're going to use an approximation, which I'll just put it in red. And we're going to basically do an approximation. Maybe I should use green instead. To this multi-stage flash here, and what we're going to say is that all of the components, the light components, maybe including C5, is a little uncertain, but it could be those two. That none of those components make it into the liquid, but as soon as you get past C5, you get all of the components into the liquid phase. So you basically have a step function like that. The black one might be approximated by everything less than C4, and then the C5 and heavier is something like that. So we get some kind of a. So you see, we're making a kind of a gross approximation, but it's actually not too bad. So we can. So what we're going to say is that we approximate a process saying that the surface gas and the surface oil is given by Cn plus and Cn minus 1. So typically for a 3-stage, we use N is equal to either 5 or 6, and I'll say 6 in general. Maybe a 2 to 3 stage. You might consider bringing it to 5, but it's going to be an approximation that you can make use of. Okay. So that are there any questions about this? I mean, it's obviously an approximation, but the question is how close you're going to be to getting an easy way to go back and forth between molar composition and volumetric oil-gas ratio. So if you do this, then what you get is that you get the R is equal to volume of surface oil to volume of surface gas, where the volume of surface oil is basically equal to, now we've got the incoming well stream, molar composition, well stream composition of the N plus components times the molecular weight of the N plus components divided by the density as a surface oil, if you will. Okay, so this density is at, I'm not going to write that way. I'll just write it as a stock tank liquid. So that'd be a stock tank liquid. So you basically need the molecular weight of, for example, the C6 plus. So you would need the molecular weight, C6 plus, and the API of the C6 plus, or the density of the C6 plus to get its density approximation. And then the volume of gas would just be, now the moles of gas, the moles that become gas, is just 1 minus the well stream amount of Cn plus, right? So that's the number of moles that become surface gas times this 379, depending what unit you're going to use. That's 379 for pounds, or standard cubic feet per pound mole. So you end up with R is equal to Z well stream plus over 1 minus well stream N plus times constant. And that constant is just equal to the molecular weight over density, which is kind of a molar volume of the CN plus. And then we need to divide by that, so we basically get PSC over R TSC. And I think this is right. The oil, molecular weight, density, and that. So if you want stock tank barrels per million, for example, then you have to do some additional, you have to add some additional constants. Could someone look that up in the monograph equation number for that, and I can pull that up.
Is it 7.13?
Should be. Which equation?
7.13, I think.
$7.13.
That's in feed units.
Mm-hmm. Now here you also see the BG D and the BGW terms. In fact, I made a mistake before lunch, so I need to correct that as well. I think this is the inverse. This is the inverse of the COG. This I'm going to write COG since it's in the book. See here. 133,000. Is that it? Yeah. Okay. And I think that will have units, COG has units of standard cubic feet per stock tank barrel here. So the inverse of that up there would give you the stock tank barrels per standard cubic feet. Just a second here. Maybe I got this wrong. This is C to the minus 1 is this. should be like this.
So here the O hat is the N plus in the COG equation.
Yeah, so does it actually give it in with a hat? Yeah, exactly. It's the, so the O hat is being defined as CN plus. Okay. So this being a well stream, this would be a producing solution oil gas ratio, producing CGR. Okay. So it's just it's a simple, relatively simple way to come up with this. Now, what you can actually do is that if you do equation of state calculations with a full process and everything, you can actually correlate a certain, the C5 plus with the calculated CGR for a given process, and you can find this constant, what it should be. There's going to be some variation in this term here as you deplete a gas condensate, not a big variation, but some variation. So, but altogether, this is a useful way to translate composition to OGR and vice versa. Any questions about this or where it comes from? This is basically the physical interpretation of what's being done. Okay. All right. So now before we go any further, I've got to show you the mistake I made here. This should have been equal to NG plus NO over NG, which is equal to 1 plus NO over NG. So this is wrong. Not terribly wrong, but it's wrong. Okay, so pick that up and appreciate that. Now that also you can see in this same chapter 7, this relationship between BG and wet and BG dry. I can give that to you is also using the same COG term. You've got this equation BGD. I'll just write it here. BGD is equal to BGW, which you have in all of your textbooks, times 1 plus COG that we just defined down there, little rs. Okay. Now, the units have to be consistent here. So in this case, COG has units standard cubic feet per stock tank barrel. So the little rs would have to be given in terms of stock tank barrel per, instead of on the basis of 1,000,000 standard cubic feet. All right. So what I was telling you about the PVT lab not really giving you the information to find BGD, it kind of does and kind of doesn't, because this little rs term is related to the process, right? And the lab often does not do multi-stage separator tests of gas condensates because there's really just too little, the sample is such that there's too little liquid that when they do the flash in the multi-stage, there's just too little liquid being processed in the laboratory. So they often just don't even do it. And even if they did do it, it might be at a set of separator conditions, 2 or 3 stage, that are different than what you want to actually do your processing at. So you'll end up needing an equation of state one way or another to make this, this conversion. So the COG will be affected by the process, and the little rs will be affected by the process. And of course, so that's, any questions about this? Okay. All right, then so let's just do a simple exercise for this COOF paper, and I'm going to have everybody try to follow me. You've got this set of directories. Now, somebody needs to speak up now if you haven't gotten access to these directories. Now, you probably don't use Total Commander like here, you use Windows Explorer, but you need to see these directories, eNotes, exercises, and then the COOF and the notes and so forth, okay? If you don't see that, then you need to let us know because you're going to get behind. But I'll do the exercise myself so you can follow that. And so if you're not able to follow yourself or find it, then you can always just follow what I'm doing and correct me if I make a mistake. So what we're going to do is that we're going to go into this paper, and in that paper, the reservoir simulator data files that were used to create all of the results in this paper are given here. Black oil compositional files, compositional EOS-based compositional files, everything's given. It's using a reservoir simulator called Sensor, and I believe, if I'm not wrong, that after this paper, because I give run times in the paper for simulating the entire North Field, the run times fully compositional and black oil are given here. And I believe that Qatar Petroleum, is there Qatar Gas? No, sorry. The main operator of the field has started using Sensor, or at least did so for a number of years. So let me just go in and show you. And this was, oh shoot, this isn't good.
We have the people from Qatar Gas here. It's few people from Qatar Gas in their course.
Okay, so
maybe they can say confirm or
yeah. At least I think the independent simulations of Northfield may be using Sensor, at least did for some time. Yeah, here it is. I think it was originally using another one of Keith. This is Keith Coates who wrote Sensor. I think the early, at the time this paper was written, a program called Comp4, which was the last compositional simulator of Keith Coates before he wrote Sensor, was being used. And then,
It's a sensor.
huh?
It's a CPU time of sensor.
Yeah, so this is Sensor.
Okay, yeah.
And so this was published and giving run times that were mildly quite impressive for fully compositional and black oil runs. So anyway, that's all these files are using Sensor. So it's a very simple input file and a simple output file. That's it. Okay. So if you go into the tables directory, in the first table 1, 2, and 6, you'll find an output file. You see the one is compositional base case and the other is black oil base case. So it's this file here that you want to open. And there's black oil tables. We're not going to talk immediately in detail about the black oil tables, but we'll just pick some numbers off of this first. So everybody needs to open this now.
Open it in a text editor.
In a text editor. So if you have something other than Notepad, it might help if you're going to copy columns. You don't need to copy columns right now. You just need to be able to edit. So just use any editor. I use TextPad, but just any editor. The output file, it says NFRBO _ base, the output file. Okay. And then we search for black. Okay. Now there are 2 black oil tables in this file because 2 of the hoof formations have one composition, and then the other 2 we changed the composition to add more H2S and less methane. So if we go up here, you can see that the K1, K4 is the first table that you'll find in the output file. So this table PVT type 1, that's this first table. And the table 2 is for K2, K3, where we've basically moved 3 mol% of the methane into H2S to give a well stream with a higher H2S content. And otherwise, the compositions of all the other components are the same. If you look at, there's a nice paper in the references to this paper by Kwaku Tomang, somewhere here, talking about the spatial compositional variations in the Saudi Aramco Kuth gas condensate field. And that was published many years back, somewhere. But anyway, they talk about the variation of H2S and methane. And so this approximate treatment here was done. So they're essentially the same compositions except for methane H2S. Okay, so what you see is that in the Blackwell table, it's been created from the equation of state within Sensor automatically. So it reads in the equation of state, reads in the composition, and then it'll create internally the Blackwell table. And the Blackwell table, the saturated properties of the Blackwell table are shown here. Here you've got the little RS, solution condensate gas ratio. You can see up at the initial dew point pressure, it's got a CGR of 31 barrels per million. And the saturated BG at that dew point pressure of 5133 is given here. Okay, so what we're going to do here is calculate the initial gas in place. I don't know whether there's a pore volume given here or not. Initial pressure, water saturation, let's see, the area, is that given? Yeah.
Surface area.
This is for the entire project, 10 by 10 kilometers. Okay, we can calculate the initial gas and initial condensate in place for this surface area. So we've got the area 10 by 10 kilometers. We've got the thickness, porosity, water saturation. We'll use the K1, K4. That's got 10% porosity. Initial pressure 5315. So it's slightly undersaturated. So we're going to have to go and get the undersaturated BG at 5300 at initial pressure, 53 15. See, what about the thickness here? Yep, under the thickness. Mm-hmm.
Go down a bit. Size of total reservoir. And that's probably the last part. The height.
Is it 1721 feet? The size of total reservoir, you have the last multiplying number. That should be the thickness.
Okay, the problem will be that since there's different fluids in K1, K4, and K2, K3, we need to know the distribution of that.
You can just look at the difference in the reference depth.
Yeah. Yeah. Okay. Well, let's first find the BGI D. We need BGDI, and we need little RSI from the Blackwell tables. And it needs to be at, I think this is 220 Fahrenheit, and initial reservoir pressure of 50 315. PSIA. Dew point is given to be 5135. So from this, we can read the little RSI from the saturated tables. And it's table 1. So what was that little RSI? And then you need to go to the undersaturated Blackwell table 1 at 5315 to get the BGDI. So the Blackwell PVT table is basically separated into two tables. One is for saturated properties and the other for undersaturated properties. And that's clearly labeled in the output file of sensor here. You've got table 1, PVT type 1. You've got the saturated table. You go to the reported dew point, and you get the solution condensate gas air ratio. Okay. 31.1. Okay. So that's the saturated table. But the undersaturated table is below. So there we have to find the particular table for a particular gas. And the gas we're looking for is the gas with this 5100 dew point. So we just have to page down to get to the here's the 5133.22. That's the right gas, and we need it to be at a pressure of 5,300. So we've got it at the dew point, and we've got it at 5,500. So we have to interpolate. So BG dry at the dew point, that's 0.00071. And at 5,500, BGD is 0.000680. Interpolating, we get a BGDI at 5315. Can somebody try to do that interpolation? And I think you're fine doing it linearly. I mean, if it was a bigger pressure distance, it's better to interpolate using 1 over BGI, 1 over BG, or which we define as a term as little bg, okay? So if you flip these upside down to do the interpolation, that would give a more accurate result, because 1 over bg is approximately linear with pressure.
That's 0.000691.
0.000.
6951.
Okay, we'll take just the 3 digits is fine. Thanks. 0.00695. Thanks.
Yeah.
So we got the 2 numbers, the key numbers that they're going to fire us if we can't calculate the initial gas and oil in place correctly. Okay. So now we need the hydrocarbon pore volume, and to do that, let's actually see if they give initial. I'm going to search for initial and see. I think it gives maybe the hydrocarbon pore volume. Yeah, so equilibration, I think it's region 1 is the K1, K4, which we, okay, here we go. So K1, K4, yeah, would be these 2 here. Oops. And you've got initial fluids in place. It actually gives the BGI for us. Let's see how that compares. $695. Yeah. This is at pressure of 5284, 5164, and you see it's actually doing the interpolation for us here. And it's a little bit different because of the depth difference between K1 and K4 gives a different initial pressure. Now, what I'm a little bit curious about is the initial pressure 5315 is not here. Maybe the model wasn't initialized. At that pressure. Yeah, so you see here, it's not got 53, so I'm not sure where. Now there's 5315 and yeah, it is there. So there's a warning. Okay, maybe the 5315 is at a different reference depth. Yeah, that's probably what it is. The reference depth is 9600, whereas these are, yeah, the K1, K4, it's much shallower, so it's a lower pressure than this. Yeah. Okay, anyway, these BG values have been interpolated by the simulator at the actual pressures in the different layers. So that's the way it should be done. And these pressures are different than this 5315 because of the depths, I think. Okay. So it's a function of the composition, the initial composition, reservoir temperature, and initial reservoir pressure. This is a function of depth. So I suppose you could check these numbers here if you use the pressures that are shown over here, 5164. That's pretty close to the dew point, actually. It's real close to the dew point. So at the dew point, it was 00071, and here it's 10 00071. So basically, it's essentially it's saturated at the dew point initially, because this reservoir pressure is just above the dew point.